Imagine a white dwarf, one of the universe's most intriguing leftovers from a star's life. This small, dense object is the final form of a star like our Sun. Though it's packed with the Sun's mass, it's squeezed into a space no bigger than Earth. It shines faintly, slowly cooling over billions of years. A white dwarf is held together by a strange force called electron degeneracy pressure, a quantum effect that keeps the star from collapsing. It works because of the Pauli exclusion principle, which says no two electrons can be in the same place at the same time. As the core of a white dwarf gets denser, electrons are pushed into higher energy states, creating a pressure that holds up the star against gravity. White dwarfs are incredibly stable, some of the most reliable objects in the cosmos. But even they have their limits. This is where the Chandrasekhar limit comes in, the point at which a white dwarf can't resist the pull of gravity any longer. If a white dwarf's mass goes beyond 1.4 times the mass of our Sun, it's in trouble. At this tipping point, the white dwarf may collapse, becoming something even stranger, a neutron star. Or if it's massive enough, it might transform into the universe's ultimate monster, a black hole. But whether this star becomes a neutron star or a black hole remains a mystery. General relativity tells us that space-time should bend infinitely at a singularity, yet quantum mechanics argues that under such extreme conditions, particles and fields can't be properly described without factoring in quantum effects on gravity. This is where quantum gravity comes into play, a theory that bridges the gap between the two pillars of our understanding, general relativity and quantum mechanics. In this space documentary, we'll dive into the fascinating world of quantum gravity, exploring its concepts while also delving into the theories of general relativity and quantum mechanics. In the 1600s, scientists began asking big questions about space and time. They started to explore the very fabric of the universe, driven by a desire to understand how everything fits together. The answer to this question might have seemed straightforward at the time, but Einstein later revealed that it was anything but simple. He showed that challenging established ideas could lead to a deeper understanding of the universe. Starting his journey at just 26, Einstein made groundbreaking contributions to science, but his work wasn't finished. There was still one crucial step to take. In his book, Relativity, Einstein noted that Newtonian physics, which was developed by Isaac Newton in the 17th century, relied on the idea that space and time were independent, unchanging realities. This classical view suggests that space is like a container, and time is like a ticking clock that continues regardless of what happens in the universe. According to this view, if you removed all matter from the universe, this empty container of space and time would still exist. But this idea raises important questions. If everything we know exists within the universe, how can the universe itself exist within something else? It's like trying to imagine seeing the entire universe from a God's eye view, a perspective that's impossible to grasp. While it might be tempting to dismiss these ideas as purely philosophical, they challenge us to rethink what we know about reality. Absolute space and time may seem consistent with our everyday experiences. Objects stay where we leave them. Our commutes follow the same paths, and mornings come every day. But Einstein's work urged us to question even the most familiar aspects of our world. In truth, we never actually see objects staying still. They're always moving relative to each other, a concept known as relative motion. This motion occurs in a space and time defined only by the relationships between objects, something even Newton acknowledged in what he called our vulgar experience. We often use coordinate systems like x, y, and z axes to track an object's movement. While this seems scientific, these systems are entirely arbitrary. For example, on Earth, we use latitude, longitude, and time based on the planet's motion. These systems feel natural to us, but they're only one way of looking at things. Imagine an object moving in a straight line. Is it really moving, or is the space around it moving? It's all relative, and there's no way to definitively say what's actually in motion. This leads to the idea that there's no absolute coordinate system or ultimate frame of reference in the universe. No God's eye view. Any concept that can't be observed or tested is considered metaphysical, beyond physics. So why did Newton stick to absolute space and time? Because it allowed him to create simple and successful laws of motion. But by the end of the 19th century, scientists began to challenge these unobservable concepts, pushing for a science grounded in empirical evidence. In 1855, James Clerk Maxwell changed everything. He published papers that described electric and magnetic fields as two distinct but closely connected forces. We can visualize these fields with lines stretching from positive to negative, or from north to south poles, just like the magnetic field you feel when trying to push the north poles of two magnets together. Maxwell's work wasn't just about objects moving in space and time. It was about a new kind of physics. He showed that magnetic fields exist even in empty space, and that these fields could move in waves, much like how ripples spread across a pond when you throw in a stone. These waves, Maxwell realized, travel at the speed of light, revealing that light is just one form of electromagnetic radiation. However, this breakthrough led to confusion. Waves usually travel through something, a medium like water, for ripples. Maxwell and others thought electromagnetic waves must also move through a medium, which they called the ether. This ether was believed to fill all space and serve as the backdrop for light waves. But when scientists tried to detect this ether by measuring the speed of light in different directions, they found no difference. The speed of light was constant, suggesting that there was no stationary ether at all. This finding was puzzling because it challenged the idea of absolute space and the ether itself. This kind of puzzle is what makes science so thrilling. Newton's laws demand an absolute space and time, while Maxwell's electromagnetic waves suggest a stationary ether. But experiments show no evidence of either. What now? In 1905, a young Einstein working at the Swiss Patent Office tackled this problem with a fresh perspective. He proposed that understanding physics requires focusing on the observer, someone or something making measurements with a ruler and a clock. Unlike Newton, who treated the observer as an outsider, Einstein placed the observer at the center of reality. Einstein introduced two key principles. First, the principle of relativity. No matter how fast you're moving, the laws of physics remain the same for everyone. This means true equality in the world of physics. Second, the speed of light is constant, regardless of the motion of its source. Light from a flashlight on a moving ship still travels at the same speed, not faster because of the ship's motion. Einstein accepted this constant speed of light as a fact and explored its consequences. One of the most profound realizations was that there can be no such thing as absolute time. The speed of light, though incredibly fast, isn't infinite, which means that our perception of events in space and time is influenced by this finite speed. This discovery reshaped our understanding of the universe and laid the foundation for modern physics. The principle of relativity requires that the laws of physics be the same for everyone, regardless of their relative motion. We can't use physical measurements to determine who is moving. There's no absolute simultaneity or a privileged reference point. Events can happen at different times depending on the observer's frame of reference. As a result, time is relative, and we perceive events differently because of this. Then came the year 1905, when Einstein published an addendum to his relativity paper applying his theory to an object emitting two equal bursts of light in opposite directions. He found that the total energy of these light bursts, when observed from a moving frame of reference, appears larger, similar to time dilation. Since energy must be conserved, this extra energy doesn't come from the object's motion, but from its mass, which decreases according to the formula E equals mc squared, one of the most important equations in human history. Einstein's theory answered many questions but had limitations. It couldn't handle systems experiencing acceleration. While we might accept the relativity of uniform motion, acceleration is something we can feel, like on a roller coaster. This raised questions about acceleration and rotation, relative to what? Despite the success of his special theory, Einstein hadn't fully dismissed absolute space and time. There was more to consider. Newton's law of universal gravitation, which describes gravity as a force proportional to mass and inversely proportional to distance squared, also faced criticism. Unlike the forces in Newton's laws of motion, which involve direct physical contact, gravity seemed to act instantly at a distance, an idea that critics saw as mysterious. Newton himself admitted he couldn't explain how gravity worked. Special relativity couldn't handle acceleration or account for Newton's force of gravity, leaving Einstein with much more work to do. The 20th century didn't just bring one revolution in physics, but two. During the first, Einstein's theories of relativity reshaped our understanding of space, time, and mass energy. Yet even with the groundbreaking E equals mc squared, interactions within spacetime still follow classical rules, much as Newton and Maxwell envisioned. The second revolution in 20th century physics completely redefined our understanding of matter, radiation, and energy, even changing how we interpret the mass in the equation E equals mc squared. This revolution ushered in the era of quantum mechanics. The birth of quantum theory is a story of bold innovation and groundbreaking discovery. It begins with Max Planck's pioneering work, where he introduced the concept of quanta, discrete packets of energy that make up electromagnetic radiation. But it was Albert Einstein who truly propelled the quantum revolution forward with his daring hypothesis that light itself is composed of these tiny, indivisible bundles of energy, now known as photons. The double-slit experiment confirmed the wave nature of particle. The experiment worked as a catalyst for quantum mechanics. In 1905, Einstein proposed that light might be composed of particles, known as quanta. This idea challenged the traditional understanding of light as a wave, suggesting that it could exhibit both wave-like and particle-like behavior. Building on this concept, French physicist Louis de Broglie took a bold step in 1923. He hypothesized that small particles of matter, such as electrons, could also exhibit wave-like properties. Just as light can be focused into a beam, electrons can be formed into a beam as well, similar to the technology used in old-fashioned television tubes. In the double-slit experiment, something strange happens. Before we observe a particle, it exists in multiple possible states. But once we observe it, the particle instantly settles into a single state. This is called the collapse of the wave function. Einstein wasn't fond of this idea. The collapse of the wave function would have to happen instantly, which seems to go against his theory of special relativity, which says nothing can travel faster than light. This collapse could even affect things over great distances. There's also an issue with how quantum probability is understood. In classical physics, cause and effect are straightforward. If we do one thing, a specific outcome follows. But in quantum physics, if we do something, different outcomes are possible, each with a certain probability based on the wave function. Einstein wasn't comfortable with this uncertainty, famously objecting to the idea of randomness in the universe. If we have no proof that wave function collapse really happens, why assume it only occurs at the microscopic level? What if it only happens when we observe it? This idea is central to Schrödinger's cat paradox, where quantum probabilities apply not just to atoms but also to a cat in a box, making it both alive and dead until we look. When we observe, the wave function collapses and the cat's fate is decided. Heisenberg's uncertainty principle also limits how precisely we can measure quantum particles like electrons. When Heisenberg introduced the uncertainty principle, he believed that at the quantum level, any attempt to measure something would disturb it in an unpredictable way. No matter how advanced our methods, they would always be too clumsy, leading to uncertainty. This, he argued, is why we can't simultaneously measure an electron's path and see an interference pattern. He thought the uncertainty principle limited what we can measure. However, Bohr disagreed. He believed that our classical concepts of waves and particles are just tools to describe experiments, not the true nature of the electron. Depending on how we measure it, the electron behaves either as a wave or a particle, but we can't fully define what it really is. Bohr saw these different behaviors as complementary, not contradictory, and argued that the uncertainty principle limits what we can know, not just what we can measure. This idea became central to the Copenhagen interpretation of quantum theory. In the two-slit experiment, if we don't track the electrons' paths, they behave like waves. But if we try to observe how this wave behavior occurs, the electrons behave like particles. These behaviors are complementary but can't be observed together in the same experiment. Heisenberg's idea suggested that electrons do have precise properties, like position and momentum, and we could measure them if our experiments were more refined. But Bohr disagreed, believing that this isn't about how clever our experiments are, it's about the fundamental nature of reality at the quantum level. Some experiments simply can't be conceived because of this. The problem is deeply complex. Attempts to address the collapse of the wave function and complementarity have led to many alternative interpretations of quantum theory. Some suggest hidden variables might explain wave-like or particle behavior. These could be local, affecting individual particles, or non-local, involving a pilot wave guiding particles along predetermined paths, suggesting both wave and particle characteristics, not just one. Einstein explored these ideas in 1927 but dismissed them as too cheap. Instead of solving these issues, he challenged quantum theory with thought experiments to show it was either inconsistent or incomplete. Bohr defended the Copenhagen interpretation, even using Einstein's own general relativity against him. Bohr's argument depended more and more on the idea that measuring something always disturbs it, even though he had criticized this before. To challenge this, Einstein came up with a new idea. He described a situation with two particles that are connected, where their behavior is described by a single wave function, covering all possible outcomes of future measurements. These particles have linked properties like up and down, but according to the Copenhagen interpretation, they don't have set properties until they are measured. Once measured, the wave function collapses, and certain outcomes happen based on their chances. The cleverness of this challenge lies in how the particles are connected. By measuring one particle, we can instantly know the properties of the other, no matter how far apart they are. This means we can find out a particle's properties without disturbing it, thanks to entanglement. In theory, we could wait until one particle is on the other side of the universe before measuring the other. But this raises a question. Does the wave function collapse instantly across the universe to fix the other particle's properties? According to scientists, this idea seems unreasonable. It makes more sense to assume that the properties of the particles are set from the moment they are created. One is up and the other is down. Measuring one just reveals what was already true. But if we want to believe this, we would need to consider an alternative theory involving hidden variables. If hidden variables do exist, they would lead to predictions in entangled particle experiments that conflict with those of quantum theory. We don't need to specify what these hidden variables are to assume they make the particles locally real, acting as independent entities with defined properties until detected. However, quantum theory posits that these particles are non-local, described by a single wave function. This contradiction underlies Bell's theorem. Bell's ideas were published in 1966, and by the early 1980s, experiments by Alain Aspect and colleagues testing Bell's theorem with entangled photons strongly supported quantum theory. Local hidden variable theories are based on two key ideas. The first idea is that when we measure one particle, it doesn't affect the measurement of another distant particle. The second idea is that how we set up our equipment to measure the first particle doesn't change the outcome of the second particle's measurement. If we drop the second idea but keep the first, we get a theory where the setup can influence the measurements, just as Bohr suggested. This means that the wave function might somehow know what's going to happen, getting rid of the idea that it suddenly collapses. However, this still leaves some mysterious or spooky aspects. Leggett found that even with these adjustments, the theory still couldn't explain all the predictions of quantum theory. Like Bell in 1966, another scientist came up with a way to test these ideas experimentally. The question boils down to whether quantum particles, like electrons, have their properties before we measure them. The result shows that no matter what we do or how strange our idea of reality becomes, we can't avoid the need for the wave function to collapse. This has turned into a really complex issue. Maybe the collapse is actually a real physical event that happens when conscious beings decide to observe it. In this view, we're combining the deep mystery of quantum mechanics with the even deeper mystery of consciousness. Or maybe the collapse never happens, and instead, the entire universe splits into parallel versions of itself. In one of these many worlds, the electron is here, the cat is alive, eventually to find love. In other worlds, the electron is there, the cat is dead, and Gwyneth Paltrow misses the train and lives to tell a different story. Is there a better explanation? Perhaps a theory of quantum gravity could provide some answers. In classical general relativity, black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape. However, the singularity at the center of a black hole, where densities become infinite, poses a problem for general relativity, as the equations break down. As per the theory of general relativity, space-time is influenced by the presence of mass and energy. However, this approach can only deal with macroscopic objects. At incredibly tiny scales, every elementary particle behaves in unexpected ways. Einstein tried to address this by proposing various theories, but none provided a complete solution. Then, in the 1990s, 3 physicists introduced a fresh and innovative approach, called loop quantum gravity. The theory suggests that at the Planck scale, space isn't smooth, but made up of discrete units, or quanta. These quanta form the loops that are the building blocks of space, creating a structure more like interlinked chainmail than a woven fabric of continuous threads. This model suggests that space isn't infinitely divisible. At the Planck scale, there's a smallest possible area and volume that cannot be made smaller. The everyday areas and volumes we experience are built from these tiny units. The fact that space seems continuous to us is because these smallest units are extremely small, much like how a flashlight's beam seems smooth, even though it's made up of individual photons. At these tiny scales, space-time is believed to be bumpy and chaotic, very different from the smooth space-time described by general relativity. 𝗁𝐞𝐥𝐝 proposes that at the smallest scales, space-time is made up of tiny discrete units. This is similar to how in quantum mechanics, the energy levels of an atom are not continuous but come in specific, separate amounts. To better understand this, imagine the difference between a smooth, flowing river and a staircase. In classical physics, space-time is like the river, smooth and uninterrupted. But in 𝗁𝐞𝐥𝐝, space-time is more like the staircase, where each step represents a tiny, indivisible unit of space or time. You can't have a step that's smaller than the smallest step, just like you can't have a unit of space-time smaller than the smallest possible unit defined by 𝗁𝐞𝐥𝐝. This smallest possible unit is related to what's known as the Planck scale. The Planck scale is an incredibly tiny scale of length, time, and energy, far smaller than anything we experience in our everyday lives. At this scale, the effects of quantum gravity become significant, meaning that the usual rules of physics as we know them start to change. The Planck length, for instance, so small that if you enlarged a proton to the size of the universe, the Planck length would still be tiny in comparison. In 𝗁𝐞𝐥𝐝, the quantization of space-time geometry means that properties like area and volume can't take just any value but are limited to specific, discrete values. This is somewhat like how a digital image is made up of pixels. Each pixel represents a tiny, distinct part of the image, and together they form the complete picture. Similarly, the tiny units of space and time in 𝗁𝐞𝐥𝐝 form the fabric of the universe. Because of this quantization, space-time at the Planck scale isn't smooth, but instead has a granular structure, often described as frothy or turbulent. This means that if you could zoom in to this incredibly small scale, you would see that space-time is constantly fluctuating, with tiny loops and twists that give it a dynamic, ever-changing character. This is in stark contrast to the smooth, continuous space-time described by Einstein's theory of general relativity, which works well at larger scales but breaks down when dealing with these extreme quantum effects. The idea of quantized space-time also leads to some intriguing possibilities about the nature of the universe. For instance, because there is a smallest possible unit of space and time, it suggests that the universe has a fundamental graininess to it. This challenges our traditional notions of a smooth, continuous universe and opens up new avenues for understanding the very fabric of reality. Also, when applied to black holes, the loop quantum gravity proposes that instead of collapsing into an infinitely dense singularity, the core of a black hole would reach a point where space-time's quantized structure becomes dominant. At this point, the extreme gravitational forces would not crush matter into an infinitely small point. Instead, the quantized nature of space-time would create a kind of quantum loop structure at the core. Once space-time's quantized structure takes over at the core of the black hole, our understanding of what happens changes. Instead of collapsing endlessly into an infinitely dense point, the black hole's core is held up by this quantum loop structure. In this scenario, the intense gravitational forces are balanced by the quantum properties of space-time, preventing further collapse. This means that rather than a singularity, the black hole might have a core with a finite, though extremely small size. This core could be composed of highly compressed quantum space-time loops, which resist being squeezed into a smaller volume due to their discrete, indivisible nature. The theory of general relativity hits a wall when it comes to the information paradox, leaving us with one of the biggest mysteries in physics. But this is where loop quantum gravity comes in, offering a thrilling new perspective. Let's dive deeper into the enigma of black holes and uncover how loop quantum gravity could rewrite our understanding of the universe. Hawking discovered that the event horizon of a black hole, its mysterious boundary, can only expand, or in other words, it never shrinks. When a black hole devours matter, its surface area grows accordingly. And as far as we know, whatever enters a black hole is lost to the universe forever. There's another familiar physical property that can never decrease during a spontaneous change known as entropy, the foundation of the second law of thermodynamics. Could the surface area of a black hole actually represent its entropy? In thermodynamics, an object's entropy is inversely related to its temperature, meaning if it has a temperature, it must emit radiation. But this idea seemed absurd. How could a black hole have a temperature and emit radiation? Hawking set out to challenge Bekenstein's hypothesis a few years later. Without a complete quantum theory of gravity, he opted to use general relativity to describe the black hole itself and applied quantum field theory to the curved space-time around the event horizon. What he discovered was nothing short of shocking. He found that even non-rotating black holes seem to generate and emit particles at a constant rate, and the entropy of a black hole is directly related to its surface area. Surprisingly, black holes also have a temperature and emit what we now call Hawking radiation. When matter falls into a black hole, its surface area, and thus its entropy, increases. However, its temperature decreases, which seems counterintuitive. It's like adding fuel to a furnace that gets colder with each shovelful of coal. It gets more complicated. If a black hole emits Hawking radiation, it loses energy and mass, which should cause its surface area to shrink over time. However, the entropy lost by the black hole is outweighed by the entropy of the emitted radiation. So overall, entropy still increases, preserving the second law of thermodynamics. But as the black hole's entropy decreases, its temperature rises, speeding up the emission of Hawking radiation. Eventually, the black hole evaporates completely, ending in an explosion. This raises an important point, that entropy is a way to measure disorder and shows how many different ways a complex system can be arranged. It also relates to how likely it is for the system to be in a certain state. The second law states that in a natural process, the tiny parts of a system spread out to fill more space. For instance, the air in the room spreads out evenly, which is very likely. It's very unlikely that the air would collect in one corner and cause us to suffocate. If the air molecules were to gather in one corner of the room, this would be a highly ordered state with very low entropy, which is extremely unlikely. Interestingly, researchers discovered that information is connected to the logarithm of probability, showing a direct link between information and entropy. This connection applies to all types of information, including the data encoded in the quantum wave functions of material falling into a black hole. This is related to black hole entropy and the information paradox. But this discovery creates a problem. What happens when the black hole evaporates? We might think that the information is lost forever. This creates a problem because quantum mechanics insists that all the information present at the start of a process must still exist at the end, even if it changes form. This idea is like the conservation of probability. The information can change, but it must still be somewhere. So, the idea that information is lost when a black hole evaporates goes against the core principles of quantum theory. This is known as the black hole information paradox. In a semi-classical approach, theories like quantum field theory or general relativity don't work well when a black hole is pushed to extremes. For instance, as a black hole evaporates, its surface area gets smaller, reaching a point where quantum properties must be considered. We already know that general relativity alone can't handle this situation. Therefore, we can expect that any complete quantum theory of gravity should at least approximately match this formula as a starting point. And here, loop quantum gravity is able to give explanations. It shows a simple link between entropy and area. Entropy is found by taking the logarithm of the number of possible quantum states in a system. In loop quantum gravity, the connections in the spin network show the quantum states of space. These states are controlled by tiny units of area, which are linked to the square of the Planck length. The links representing the area in the spin network are more important than the nodes representing volume, because the links pierce the black hole's event horizon and vanish beneath it. Each link adds a bit of area to the horizon, determined by its spin quantum number. The entropy is simply the logarithm of the total number of different ways to give the surface a certain area. Researchers called this the geometrical entropy. They assumed that entropy should be directly proportional to area. But when they applied this to equations, the results were not right, as per observations. After years of refinement, they revealed that the quantum states most significant in counting the punctures on the event horizon are associated with a spin network having a spin quantum number of 1 to 2. Objects with this spin can have two orientations, +half or -half, analogous to up, down, or on, off. These binary possibilities are similar to the 0 and 1 bits used in computing. They then revised their formula, stating that the entropy of a non-rotating black hole is directly proportional to 1/4 of the area, multiplied by a constant. This constant has a value of 0.23753. It was suggested that the surface area of a black hole's event horizon is made up of tiny units of space, each about the size of a square of the Planck length. Each of these units represents a bit of information hidden behind the horizon. They also concluded that if the scrambled bits of information are not lost forever, they must either be stored on the surface of the black hole and eventually released as Hawking radiation, or they are preserved in some form of the remnant left behind after the black hole fully evaporates. According to the holographic principle, the maximum amount of information that can be stored within any region of space is constrained by the amount that can be encoded on the boundary of that region. Therefore, the second scenario, which suggests that information is preserved in the form of remnants left behind, is less likely due to the limitations imposed by the holographic principle. At that time, superstring quantum theory was introduced, combining both string theory and quantum field theory. This dual nature of the theory generated a lot of excitement within the string theory community. It was found that superstring theory, which naturally includes quantum gravity, is equivalent or dual to a supersymmetric quantum field theory in a fixed space-time background, which does not include gravity. Witten further demonstrated that a black hole in the space-time of superstring theory is equivalent to a hot soup of elementary particles, like gluons, on the boundary surface. And due to this, any information that enters a black hole can still be recovered from the dual quantum field theory and is eventually released through Hawking radiation, though it is not lost. This theory also had its challenges. The main issue was that it involves superstring theory in a space called anti-de Sitter space. And in that space, we can imagine a universe as being made mostly of dark energy, with a positive cosmological constant and positive space-time curvature. In de Sitter space, the angles of a triangle add up to more than 180 degrees, which challenges our basic understanding of geometry. In contrast, in anti-de Sitter space, the cosmological constant and space-time curvature are negative, so the angles of a triangle add up to less than 180 degrees. This creates a hyperbolic, saddle-shaped universe. When matter is introduced into an anti-de Sitter universe, the curvature of space-time pushes it away from the boundary and toward the center. But this theory is still in its developing phase, and scientists are working on it. In 2014, Rovelli and 𝐓𝐴𝐷𝐴𝐷, working at the University of Nijmegen in the Netherlands, proposed that instead of collapsing into a singularity, a black hole collapses into what they called a Planck star. For a black hole with the mass of the Sun, this Planck star would have a radius of about 10, raised to the power -10 centimeters, extremely small, about 30 orders of magnitude larger than the Planck length, but still smaller than an atom. As the black hole evaporates, it likely forms a long neck, allowing it to contain all the quantum information within its horizon, preventing any loss. Rather than collapsing completely, the black hole's core bounces back due to the effects of quantum gravity. To someone on the surface of the Planck star, this bounce happens very quickly, but to an external observer, gravitational time dilation makes the bounce appear to take longer than the current age of the universe. In this scenario, there are two horizons: the outer event horizon, which shrinks as the black hole emits Hawking radiation and evaporates, and the inner horizon of the Planck star, which expands. Eventually, the two horizons meet, allowing any remaining information to escape, resolving the paradox that information might be lost in a black hole. Black holes can also form from stars much smaller than the Sun. Any black holes formed in the early universe with masses around 10 raised to the power of 12 kilograms should be evaporating now, releasing energy from their Planck stars. The death of such a primordial black hole would result in a brief burst of intense, high-energy radiation as the Planck star releases its energy and disappears. Signals from very short gamma-ray bursts detected by 7 different satellite-borne instruments suggest they might be coming from primordial black holes. A possible smoking gun would be observing a distinctively flattened redshift distance curve. Primordial black holes exploding now would be smaller, emitting higher frequency radiation that partially offsets the cosmological redshift. While we are still far from confirming whether these radiation bursts can be attributed to Planck stars, assuming they exist, this proposed solution to the information paradox gives us something tangible to investigate rather than just speculate about. The fundamental nature of our universe, as understood by both relativists and string theorists, is grounded in quantum fields. While quantum field theory doesn't account for every aspect of reality, such as human evolution or consciousness, it does explain the core fabric of physical reality: space, time, matter, and energy. At its most basic level, everything is reducible to quantum fields and their interactions. The standard model of particle physics uses quantum fields to describe elementary particles and forces, while loop quantum gravity suggests that space-time itself arises from a separate, background-independent quantum field. The independent quantum field, known as graviton field, sits on a flat background space-time. It is thought to be the cause of the space-time curvature that we recognize as gravity in the context of general relativity. The particle theorists argued that if loop quantum gravity is indeed a quantum field theory, then there should be particles, or quanta, associated with this field. So, where are these particles? The standard model of particle physics explains that forces between particles, like quarks and electrons, are mediated by specific force particles. For instance, the photon carries the electromagnetic force between positively and negatively charged particles. This is a long-range force, transmitted by massless photons, the quanta of the electromagnetic field. The W and Z bosons, which are heavy particles, transmit the weak force between different types of quarks and leptons, such as electrons and neutrinos. This weak force acts over a short range, mainly within the nucleus. Gluons, on the other hand, carry the strong force, also known as the color force, between quarks of different colors, like red and blue. Although this force is short range as well, it behaves differently, with gluons being massless, like photons, and serving as the quanta of the color field. Given this understanding, it's difficult to dismiss the idea that gravity, like other forces, must be transmitted by force carriers, or quanta, of the gravitational field. If gravity is indeed a quantum phenomenon, as many theorists believe, then a fundamental particle should exist. The fundamental particle is termed gravitons. Since gravity is a long-range force, this implies that gravitons are massless, and their nature suggests they should be tensor bosons with a spin of 2. Although this is all very persuasive, this is not the conclusion of loop quantum gravity, LQG. The fundamental quanta that emerge from this formulation of the quantum theory of gravity are not gravitons. Instead, they are quanta of the area and volume of space. These very different views are difficult to reconcile. Particle theorists see the graviton as essential in any quantum theory that purports to describe the force of gravity. In contrast, general relativity does not interpret gravity as a force at all, but rather as a secondary consequence of the distortion of space-time geometry or the gravitational field by the presence of mass energy. Of course, this doesn't mean that changes in the gravitational field have no physical effect. They do. Suppose if the sun were to suddenly vanish, the disturbance in space-time would take 8 minutes to reach Earth, just as a disturbance in the electromagnetic field would. We would feel the change in gravity and see the sun's disappearance simultaneously, as both disturbances travel at the speed of light. The electromagnetic effect is carried by the electromagnetic field, while the gravitational effect is carried by space-time. So the gravitational field will have a physical effect. In simple terms, when we try to understand how gravity works in the tiniest parts of the universe, it's not surprising that the usual ideas we have about gravity don't include a specific particle called the graviton. Instead, in this way of thinking, there's no force that needs to be carried by a particle. But that doesn't mean the graviton isn't important in all theories. In loop quantum gravity, for example, gravitons can still play a role. Just like how light can be seen as both a wave and a particle, in quantum mechanics, what we think of as particles are really just tiny vibrations of energy, not solid objects. But this idea that things can be both waves and particles isn't just for tiny particles. Anything at the atomic level that acts like a wave can also be thought of as particles. For example, if a wave carries energy, we can think of it as having a certain mass. Even though saying a wave has mass sounds strange, it's easier to understand if we think of mass as a property of particles. We usually don't think of big waves, like ocean waves, as being made of particles. But when we look at tiny things, like atoms, the idea that waves can also act like particles becomes important because of something called Planck's constant. Some solids and liquids are made of atoms arranged in a grid-like pattern. These atoms aren't completely stuck in place. They can wiggle a bit. When one atom moves, it can pass that movement to nearby atoms, creating a vibration that moves through the grid like a wave. These vibrations can be thought of as waves with different frequencies, but in quantum mechanics, we can also describe them as particles. In 1932, a physicist named Igor Tamm called these particle-like vibrations phonons because some of their vibrations are in the range of sound waves. Phonons are not basic particles and don't carry forces like photons do, but they act like particles in certain situations. Let's talk about gravity again. When scientists detected gravitational waves in 2015 with LIGO, it was a big deal. But many physicists who understood general relativity and black holes expected this would happen eventually as our technology got better. In quantum mechanics, we can describe waves as particles, and for gravitational waves, these particles are called gravitons. This idea helps because loop quantum gravity predicts that space itself is made up of tiny, discrete pieces. These pieces are connected in a network, and as they change or jump from one state to another, they create the fabric of space-time, which has a natural grid-like structure due to the quantum nature of space. This is different from the imaginary grid we use in some physics calculations. The natural grid in space that emerges in loop quantum gravity is dynamic, not fixed. Gravitational waves can be thought of as vibrations moving through this space grid, with gravitons acting like particles that represent these vibrations, similar to how phonons represent vibrations in solids or liquids. So, if the sun suddenly vanished, the change in gravity would be carried by gravitational waves, taking 8 minutes to reach Earth. These waves can be thought of as massless gravitons traveling at the speed of light. In conclusion, we can reasonably infer that when we detect gravitational waves, we're actually detecting a large number of gravitons, and this might eventually help us learn more about their properties. However, since it's practically impossible to detect individual gravitons, the idea of a graviton as a particle of the gravitational field remains purely theoretical for now. To put it simply, we could say that the quantum nature of space and time in loop quantum gravity only appears at the tiny Planck scale. The standard model, which explains particle physics, operates on much larger scales, so space-time is usually treated as a smooth, continuous backdrop. However, this explanation isn't enough. If we believe 𝐓𝐞𝐥's description of space and time at the Planck scale, theorists must show how the familiar particles and forces we know emerge from this quantum structure. As physicist Carlo Rovelli said in 2011, a theory that can't make calculations isn't a good theory. As per him, calculating anything in quantum gravity is extremely challenging. Einstein realized he could apply his general theory of relativity to the entire universe, even though this was a bold and risky idea. According to the standard model of inflationary Big Bang cosmology, the universe began with a hot Big Bang, a sudden explosion of space, time, and energy around 13.8 billion years ago. Supporters of this model argue that it solves the flatness and horizon problems by proposing a brief period of rapid exponential inflation occurring between about 10 to the power minus 35 seconds and 10 to the power minus 32 seconds after the Big Bang. This rapid expansion imprinted quantum fluctuations from the inflaton field onto the universe's structure, leaving detectable traces such as tiny temperature variations in the cosmic background radiation. This model isn't complete on its own. We need to add two crucial but mysterious components: dark matter and dark energy, which make up 95% of the universe's mass energy. Dark energy appears as a small, positive cosmological constant, causing the universe's expansion to accelerate. The model is both satisfying and frustrating. With just 6 parameters, it explains many different cosmological observations and unites them into a coherent picture. However, we still can't explain most of the model, and our theories break down at the very beginning, the moment of the Big Bang, where all known physics fails. This occurs because general relativity is a classical, non-quantum theory, which allows for things to be infinitely large or incredibly small. In the Big Bang, this idea shows up as a singularity, a point where the universe's mass-energy density is infinitely large and the entire universe is compressed into something infinitely tiny. A singularity is actually quite problematic. Some theorists suggested that singularities occur due to the highly symmetric nature of the space-time metrics used in solving Einstein's gravitational field equations, and that these singularities might not appear in less symmetric solutions. However, in 1970, a set of singularity theorems was developed, showing that when general relativity is applied to extreme conditions of mass-energy density and space-time curvature, the formation of a singularity is unavoidable. The prediction of a Big Bang singularity means we can't even ask basic questions about the origin of everything, let alone answer them. This is just the start of the issues. While cosmic inflation solves the flatness and horizon problems, it still leaves us puzzled about the initial conditions and how long inflation had to last to create the universe we see. It solves one fine-tuning problem but creates another. Some theorists now suggest that recent data on cosmic background radiation challenges the simplest inflation models. Additionally, current theories can't explain why the cosmological constant has its specific value. Let's address these issues one by one. When loop quantum gravity emerged as a consistent theory of quantum gravity in the late 1990s, it raised questions about our understanding of the universe's earliest moments, especially regarding the Big Bang singularity. As noted, the Big Bang is a prediction of general relativity in a realm where it breaks down. This incompleteness of general relativity was recognized earlier. Early attempts with quantum geometrodynamics and the Wheeler-DeWitt equation didn't offer new ways to solve the problem. It was believed that a complete quantum theory of gravity should remove singularities, but in 1988, there was no clear method to build such a theory. For 11 more years, the issue remained unresolved. Then, a young PhD student from the University of Aachen published papers that created quite a buzz. Though technical, these papers showed that a quantum cosmology could be developed using loop quantum gravity. The excitement was palpable when it became clear that the discrete nature of space in loop quantum gravity might eliminate the Big Bang singularity. If successful, this could mean that loop quantum cosmology could be valid all the way back to the very beginning of time. After completing his PhD in 2000, a researcher was brought to Penn State as a postdoc to tackle this challenge. He aimed to find out how quantum geometry affects the classical Big Bang singularity. The solution involved some assumptions and complex mathematics, but he ultimately found that quantum geometry introduces effects that remove the classical singularity. Einstein's gravitational field equations can represent different types of space-time metrics. In cosmology, these solutions are expressed using the cosmic scale factor, symbolized as alpha. This scale factor measures the proper distance between 2 points, like galaxies, at a given time, compared to this distance at an earlier time. As the universe expands, this distance grows, making the scale factor time-dependent. If the universe expands forever at a constant rate, the scale factor increases linearly with time. This concept is the basis for Hubble's law, which states that a galaxy's speed of moving away from us is directly proportional to its distance from Earth. In Hubble's law, the constant of proportionality is known as the Hubble parameter. This parameter is the ratio of how the scale factor changes over time to the scale factor itself. Think of this change in the scale factor as the rate of expansion or contraction. In a universe expanding at a constant rate, this rate is constant and positive. In a contracting universe, it is constant and negative. However, our universe's expansion rate is not constant. It is accelerating, which means the Hubble parameter changes over time. The Hubble constant is the value of the Hubble parameter at the present time. It was soon discovered that the early solutions to loop quantum cosmology had some unrealistic implications for the Hubble parameter. However, interest continued to grow as loop quantum gravity techniques were applied more systematically in cosmology. Researchers developed more refined models. These researchers created detailed mathematical structures and used computer simulations to find solutions. They could run these simulations forward or backward in time. To explore what might have happened around the time of the singularity, they ran the simulation in reverse, observing space-time contracting toward a big crunch. To their surprise, instead of collapsing into a singularity, the universe began to expand again. This resulted in what is called a cosmic bounce. The Model 2 faced issues despite showing promise in solving the singularity problem. Although initially discouraged, researchers continued refining the model. They discovered 3 unphysical aspects and realized that a shift in perspective from area to volume was needed. Over about 6 years, the model evolved through 4 stages before being considered physically sensible. The good news was that the concept of replacing the Big Bang singularity with a big bounce remained valid. In a simplified approximation of the full quantum version, the effects of quantum geometry appeared as a correction to classical general relativity. This model allowed for precise answers to many questions. The resulting loop quantum cosmology, 𝐓𝐿𝐶 solutions, closely resembled those from general relativity, with an additional quantum correction term. This term involves the density of mass energy in the universe compared to a critical density. The negative sign is crucial. In a contracting universe, when the density reaches the critical level, the equations balance out and the universe stops contracting. The research is still ongoing, and maybe we will be able to understand the complex singularity of the Big Bang along with the black holes with help of quantum field theory. As researchers continue to refine loop quantum cosmology, the prospect of resolving the Big Bang singularity and understanding the universe's earliest moments grows increasingly promising. While challenges remain, the progress made so far suggests that a quantum theory of gravity may yet reveal the secrets of the cosmos. As scientists push the boundaries of human knowledge, one thing is clear: the intersection of quantum mechanics and general relativity holds the key to unlocking the mysteries of the universe, and the journey to uncover them has only just begun. At the quantum level, the formation of our solar system can be understood by exploring the fundamental principles that govern the behavior of matter and energy in the universe. Quantum mechanics, the branch of physics that deals with the smaller scales of energy levels of atoms and subatomic particles, plays a crucial role in the processes that led to the birth of the solar system. The story begins in the early universe, shortly after the Big Bang. The universe was in an extremely hot and dense state, and quantum effects were dominant. During this time, all 4 fundamental forces – gravity, electromagnetism, the strong nuclear force, and the weak nuclear force – were possibly unified into a single force due to the high energy levels. As the universe expanded and cooled, these forces separated, with gravity eventually playing the most significant role in the large-scale structure formation. Quantum fluctuations in the early universe are critical to understanding how the solar system eventually formed. These fluctuations were tiny variations in the density of matter, and they were stretched to macroscopic scales during a period known as cosmic inflation, which occurred just fractions of a second after the Big Bang. These minute differences in density provided the seeds for the formation of galaxies, stars, and solar systems. As the universe expanded and cooled further, matter began to clump together under the influence of gravity, eventually leading to the formation of large-scale structures. Within these clumps of matter, quantum processes continued to play a vital role. The gas clouds that would eventually form stars, including our Sun, were influenced by quantum mechanical effects such as quantum tunneling and quantum electrodynamics. Quantum tunneling is a phenomenon where particles can pass through potential barriers that they would not be able to overcome in classical mechanics. This effect is particularly important in the nuclear fusion processes that power stars. In the core of a star, temperatures and pressures are so high that hydrogen nuclei, protons, are forced close enough together that quantum tunneling allows them to overcome their mutual electrostatic repulsion and fuse into helium. This fusion process releases vast amounts of energy, which counteracts the gravitational collapse of the star and leads to the stable, long-lived stars that form the centers of solar systems. As the proto-sun formed in the center of a collapsing gas cloud, a protoplanetary disk of gas and dust formed around it. Within this disk, quantum mechanics governed the interactions between particles, leading to the formation of larger bodies. For example, the process of accretion, where dust grains collide and stick together to form larger particles, is influenced by the quantum mechanical forces between atoms and molecules. These forces, described by quantum electrodynamics, determine how particles interact and bond at the smallest scales. As these dust grains grew into larger and larger bodies, they eventually formed planetesimals, small, solid objects that are the building blocks of planets. The continued collisions and mergers of planetesimals, driven by gravitational interactions and influenced by quantum effects at the atomic level, eventually led to the formation of planets, moons, and other bodies in the solar system. Another important quantum mechanical process in the formation of the solar system is the creation of the elements that make up the planets and other bodies. In the cores of stars, nuclear fusion processes, governed by quantum mechanics, create heavier elements from lighter ones. For instance, in massive stars, fusion can produce elements as heavy as iron. When these stars reach the end of their life cycles, they often explode in supernovae, scattering these elements into space. The heavy elements formed in these stellar explosions, such as carbon, oxygen, and iron, are crucial for the formation of rocky planets like Earth. The processes that lead to the creation of these elements, including nuclear fusion and neutron capture, are fundamentally quantum mechanical in nature, relying on the principles of quantum chromodynamics, which describes the interactions between quarks and gluons in atomic nuclei. In addition to quantum mechanics playing a role in the formation of planets, it also influenced the early evolution of the solar system. For example, the stability of planetary orbits is a result of the interplay between gravity and the quantum properties of matter. The distribution of mass and energy in the protoplanetary disk, shaped by quantum processes, affected the eventual arrangement of planets in the solar system. Even after the solar system formed, quantum mechanics continues to play a role in its evolution. For example, the energy levels of atoms and molecules in the atmospheres of planets and moons are determined by quantum mechanics, which in turn affects their thermal properties and chemistry. The behavior of magnetic fields in planets, which can protect atmospheres and surface conditions, is also influenced by quantum effects, particularly in the dynamics of charged particles and the generation of magnetic fields through quantum electrodynamics. At its core, the formation of our solar system can be traced back to the fundamental principles of quantum mechanics, from the quantum fluctuations that seeded the initial density perturbations in the early universe to the quantum tunneling processes that drive nuclear fusion in stars. Quantum mechanics underlies many of the processes that led to the birth and evolution of our solar system. Without these quantum effects, the universe as we know it, with its galaxies, stars and planets, including our own solar system, would not exist. So this is the end of our video. I hope you liked the information and value provided in this video, and if you did, kindly hit the subscribe button.